Okay, so in this section, we're going to be talking about the connection between the stars, the sun, and time. So the first thing I would ask you to think about is what is time, and why do we keep time, and how would we define a day, a month, a year? And if one turns out to give you, come up with answers um, like, well, there are 24 hours in a day, uh, and uh, then I would ask you, well, what is a day? And then you would say 365 days in a year. Then I would ask you, what is a year? Um, and we could go on and on and on with this sort of thing until you came upon the idea that we're looking at cycles in time. We're looking at the position of the sun relative to the stars in the night sky, the position of the sun relative to when it will reappear in that location. And it turns out that our day is defined mostly in terms of when the sun rises and the sun sets. At least that's how it started. And when we have 365 of these transitions between day and night and back to day, then we notice that when the stars rise, that the stars rise in the same place as they did 365 years before. Now, the same sort of thing applies to a month. The month is defined by how the moon moves through the sky. And so we notice that during the course of a month, through 28 days, that the moon goes through its entire set of phases. So we go from a new moon to a new moon in 28 days. So that's the basis of how it works. Now, to talk about this, I would be remiss if I didn't tell you the difference between revolution and rotation. So the rotation of an object about its axis is different than its movement around another object. So when we're talking about the seasons and the months and the days, we're really talking about the motion of the Earth, the Sun, and the Moon. How do we know that the Earth rotates? Well, it's this experiment here, Foucault's pendulum. I can demonstrate this to you in classroom time, and you can do that too. Is get a ball, attach a string to it, and cause it to swing up and down. That's called a pendulum. And then hold it above you so it doesn't hit you, and then get into a chair that you can rotate about. And then rotate that chair about and notice the motion of the pendulum. You'll notice that the pendulum continues as it was moving before, north or south or east or west. And then even though you rotate the pendulum, you rotate the pendulum because you're sitting in the chair and you're rotating yourself in the chair, then it will continue to move north or south. It will refuse to change direction. And that's what we notice with such a situation here. There are several of these pendula in the, some universities have these. The Griffith Observatory has one, and you'll notice that in some of them they have little pegs that this pendulum ball strikes every 15 minutes or 5 or 10 minutes or something like that. And that's the basis for how we know that the Earth rotates, because if the Earth didn't move, then this pendulum would not rotate around as well. The other way that we can determine that the Earth moves is the cyclonic behavior that we have for storms like hurricanes and typhoons go in different directions if you're north or south. The next question is why we have seasons. And some of you may be under the false impression that it has to do with when we are closer to the sun or further away from the sun. I mean, after all, if you get your hand too close to a flame, then it gets warmer than when it's further away. Well, that is indeed true, but we're talking about distances that are so grand. And there's such a small deviation between 147.5 million and 152.5 million. We're talking about differences here of about 2% in distances here. And furthermore, if you look at when winter is for us, we're actually closer to the sun for us up here in the northern hemisphere. And then the question arises, if the heat, if we have summertime when we're closer to the sun, then why is it that Australia has a different set of seasons that seem to be, 6 months out of phase with respect to us? If we're closer to the sun and the Earth is only 13,000 kilometers across, I mean, it's only about, it's a lot smaller than this dot, and we're sort of this much closer than Australia, because it's tilted on its axis and all that, then why is it that we have these situations out of phase? And this picture here describes it. We have a tilt in the Earth's axis, and that is what is driving this whole situation. So over here, I have the sun, and the Earth on either side. And in June, you see that this portion is getting more light than this portion. In fact, over here, I'm not getting any at all. So, and then over here, I'm getting light all the time. So the tilting of the Earth has a couple of effects. One is, as the Earth is rotating about its axis like this, any particular position is moving up and down here, okay, then the amount of time that I spend in daytime is going to be proportional to this amount of time here, and the amount of nighttime is going to be proportional to this amount of space over on this side. And you see that this is larger than that over there. And notice for the equator, it's the same on both sides. So at the equator, daytime and nighttime are 12 hours on and 12 hours off. But up here for us, we're here at about 32, 35 degrees. And for the summertime, if I recall correctly, we're talking about 14 hours of daylight and 12 hours, and 10 hours in the wintertime. Okay, so the idea being the tilt of the Earth's axis is causing the whole thing, and it does two effects. One is the light rays are coming down more intensely than here, where there's grazing, the light is grazing on the Earth. And the other thing is I spend more time in actual daylight. The tilt remains relatively constant. Hopefully I can get these to play. So this is an example of something that's non-precessing.
Gyroscope may be a lot of fun to watch. It's no toy. And it's not designed to play games. In fact, it's designed not to precess. If a gyroscope is balanced at its own center of mass, the force of gravity won't make it precess. Even if its supports swivel in all directions, the axis will remain stable and keep the gyroscope pointed in the same fixed direction. The idea here is to design a gyroscope that hardly precesses at all. As Newton knew, spins on an axis that's tilted at 23½ degrees with respect to the perpendicular to the plane of the ecliptic. That is the plane of the Earth's orbit around the Sun. In other words, as seen from the Earth, the Sun seems to be orbiting in a plane tilted 23½ degrees to the plane of the equator, and twice a year the Sun passes directly through the plane of the equator. These points, where the Sun intersects the plane of the equator, are called the equinoxes, meaning day and night have equal length. And these points have long been vital to astronomers.
Okay, the next one I want to show you is a precessing motion. Let's see if this gets to play. And this is sort of like a top.
Precession. Easy to illustrate the fact that a spinning wheel doesn't fall. But beyond this example of life-copying animation, what's really going on here? What keeps the wheel from falling? Rotating about its axis causes the Earth to bulge slightly at the equator. The Sun's gravity, acting most strongly on the nearest bulge, exerts a small torque about the Earth's center when the Sun is on one side of the Earth. And when the Sun is on the other side, a torque in the same direction. The torque is tiny, but it's enough to make the Earth's axis of rotation precess very slowly. Very slowly indeed. One complete loop takes about 26,000 years.
And that's what we're seeing here. So it's the axis, this axis here will precess, although it precesses very, very small. Okay, so that's why I said earlier that our axis points to the North Star, or Polaris, right now. In the future, it will be pointing in a different direction. Okay, so again, during the summer solstice, up here you can see that the rays are more concentrated on the northern hemisphere and less concentrated on the southern hemisphere. For the winter solstice, it's opposite. So there's less light hitting the northern hemisphere and more light hitting the southern hemisphere. Okay, and that gives rise to the length of the day as well that I pointed out. And here is a picture of this. So every hour a photograph was taken, and this is probably the winter solstice, the summer solstice, and this is the equinoxes. And the person just took a picture for, at every 1 hour intervals. So from this, you can figure out what latitude you're at. Okay, seasons at the poles. 6 months of sunlight, or 6 months of sunlight, and then 6 months of darkness. On the seasons, 12 hours every day. Now, one can do other examples to consider other tilts. Jupiter has a tilt that's close to 0, and Uranus has a tilt that's close to 90 degrees. Seasonal tilt for for Jupiter is such that you would get no indication of seasons, but for Uranus it would exacerbate the seasonal differences. So the next question you could ask is, why isn't June 21st the hottest day of the year? And just think about the situation of you being in a hot tub. Do you as soon as you turn on the heater, do you immediately jump in? No, it's too cold then. It takes a while for the water to warm up. And the same situation is true for the Earth. There is a lag between when you're inputting the heat into the Earth, which is coming from the sun, and when it actually warms up. That's the reason why. And the same thing for cooling off. Why isn't December 21st the coldest day of the year? Turns out to be January, February are the coldest months. All right, we talked about precession already, and we've seen the videos for that, and so we'll continue on. Okay, we'll pause here, and we'll talk about keeping time in